I should be up and running. So hopefully everything's all hunky-dory. Hello, how are you doing, everybody? This is just going to be, this is not a programming stream, this is pretty much, can I minimize that? Yeah, that's good. This is just going to be me, hello. This is me kind of thinking out aloud. None of this is planned. This is me actually planning an article I want to write. And this is going to be with regards to memory allocation strategies. Now, that may sound like, yes, it says I'm programming, so should I just rechange this title? How do I do this? Like that. Programming theory, memory allocation strategies, planning. Done. Happy now? Yeah? Good. There we go. So I kind of wanted to kind of discuss what was kind of allocation strategies going on, and this is literally just, please comment as we're doing. This is a stream of consciousness, really, in a sense, about what was kind of going on. So that for me, I have kind of like a weird mental model in regards to memory allocation strategies. So there's kind of like three main things when I think about when I'm allocating memory. The first one is the size of the allocation. That's huge. So let's make that a little bit smaller. So the size of the allocation. Allocation. Qualities? I'm just going to call them qualities at the moment. So we have size, we have lifetime, and we also have usage. This third quantity is more of a secondary concern. So this is where I kind of want to just mainly, for the base of it, what I want to concentrate on is the size and the lifetime. So let's take the size and lifetime as an example. And the way this is the way I kind of think about it in my head. And it's about knowns and unknowns. So we're going to draw a little box where we're going to have the size on one side and the lifetime on the next. And then you'd have known, unknown, known, unknown. And we're going to go scroll in a little bit. This is probably not the best idea. And I really hate thick brushes, so it's probably not the best idea. So if you know the size and you know the lifetime of the thing, this is going to be pretty much, I would say, like 95% of the time. Like, you know the size of the thing, you know its lifetime. That's like 90% of the time. For most of the time, you may not know the size, but you may know the upper boundary of the size, but you know the lifetime for definite. This is probably closer to, like, I would say approximately like 4% of the time. The other one is you know the size of the allocation, but you have no idea what its lifetime is. This is very rare, but I would say this is about approximately 1%. And I'm going to explain which type of strategy you'll need to use for these. And the last one is you have no idea how the size is, no idea what the lifetime is. This is much less than 1%. So that's kind of the idea is what it is. So in here, this 1% here, this is what I would class as garbage collection. This is where garbage collection goes. Or a form of it, at least. Arc would be also acceptable. But yeah, like there. This one here, you've got reference counting. And these two are the most important ones. So literally, this is 99% of most of your allocations. So these are the ones we're only going to be caring about always the lifetime, and you've known that, but the size and the things are different. So these two most people actually know about. So most people know about garbage collection, automatic reference counting, and also reference counting. So automatic reference counting in here is, I class this as a form of automatic memory management, while reference counting can still be manual. You're just having to manually do the reference counting, if that makes any sense. So please, you haven't missed much, don't worry. Right, so this is where people say you would probably disagree on the known lifetime and unknown size. So this is where people go a little bit bizarre. Now, when I mean known size, I mean the range or / boundary. Now, this unknown size, but lifetime, I would say 40% of the time, this also includes stuff like files. Like literally loading a file would be a lot of this time. Like a lot of the time you don't know how big a file is when you're loading it and reading it, but you know how long you're going to be using that for. Like you're sometimes just reading it, so the lifetime is going to be quite short. It's probably going within that procedure scope or such, or even just within a certain cycle. So that's quite some stuff. So 95%, again, this is the way my brain thinks. So 95% also includes stack, the actual stack, which may sound bizarre to some people. Why do I even think about that? But that's where I'm going to go into my head. Yeah? So this is not, it's just a little bit weird table in my head. And you could think of this pretty much as kind of a weird Markov chain going on here, really, where you've kind of got most of the thing in the top left-hand corner, most in the top row and least in the bottom row. So that's kind of that little idea going in my head. But I also break this down in this top column, which is what I'll be focusing on for this kind of article I want to write, is different kind of strategies. So you have permanent allocation. So we have permanent allocation. This will be persistent for the entire program. You allocate it once, you never free. So this is never free. I'll put underneath, so this is persistent during program lifetime. So this one is permanent allocation. Okay, that's one way I think about it. Sometimes you just need to allocate all the things up front, done. The next one I have is, this is probably not the best name for it, but this is what I normally call it, is transient memory. So this is transient allocations. So a way to think about this is it is a known lifetime cycle. So this would be an LT. I'm going to put this as LT now. LT cycle. Yeah. So this would be like per frame. Oops. Or just a general loop. Something like that. Etc. Etc. So this means you allocate it, you free it at a certain point. Okay? And that's kind of how I think about it. Sometimes there are things in between these as well. So for instance, you may have permanent allocation for a transient period. So for instance, let's say you're making a game. I'm just talking about games in general for some reason. You've got memory for that level, and you've got permanent memory in that level. And that permanent memory is never going to be freed until that level is dead. So in many regards, that's classed as transient allocation, but only for that level. So it's a weird lifetime. But it's part of that level. And then you do some subsystems with inside of it, which will handle the permanent allocation. So this is I would class this as subsystem allocations. Hopefully people are following along. This is a literal train of thought, not planned out. I'm also having some whiskey. I am now trying... Which whiskey was this? What did I put on? It was... Lagavulin, that was it? Yeah, Lagavulin. Very good whiskey, actually. very good scotch. Yeah. Where was I? Yes. So we've got the transient allocations with different lifetime cycles. There's other allocations which I call scratch or temp allocations. These are similar to a transient allocation, but these are very short-lived, and these are for when I really just need some when I need some quick memory. It's like if you're writing on the back of an envelope, like you really don't want this to last long, you're just doing something really quickly. And of course, it's only a small envelope, so you can't write much on it. So this is when, for instance, a good way to think about this is, because I've been writing a lot of UI code lately, is for when I want to generate a, let's say a title or something. And I want to generate the glyphs, but the glyphs for those like text, it hasn't been determined yet. So I'm going to put that through like a printf kind of buffer thing system, where I generate to a string or a buffer, and then it's generated the text, but it's done it all through temp allocation. Don't really care. It's going to be freed straight away. It doesn't need to be. I'm only using it just to generate the glyphs, and then I won't need that string anymore. That's what Scratch is for. So this is quite a good thing. And then there's a third one which I used which is the subsystems. But these are the main kind of levels. I've described this system. This is how I think I do most of my things. Someone described this to me as manual generational garbage collection, which it kind of is. This is the way I think about problems. And if anyone can think of a better name for this, please do. But generational manual garbage collection is not a bad one. Because that's how it works in a in that one of those sort of GGC. And in the front you have different levels of tiers, and the items when they get allocated and deallocated based on how long they're used, and that we analysed by the language itself. So if they know things will persist throughout the entire program, they'll put it into a permanent allocation like slot. If they know it's going to be transient and it's just going to get allocated and freed over a certain period, they'll put it into kind of a transient slot, and different levels of those in there. And then they'll have a scratch allocation when you know it's very, very quick. For garbage collection as well, sometimes when it's when you don't know how long it's going to persist for, which is they'll put a form of what's the best way of putting it? They'll put a form of, is this clipping at all? My audio. I just realised. Sorry, there's probably a little bit too much clipping going on there. Sorry, this was when you do want small. Is that sounding better? Not as much clipping? I've just been noticing it's getting quite high. Yeah, okay. Good, audio's good. That's good to know, good to know. I've just turned it down ever so slight a touch, just because I think it was a few decibels too loud. All right, so that's kind of the first level of, I'm just kind of a bit looking at the bars on my interface. Right, so this is annoying me, the text. Okay, so there's 3 different levels of kind of allocation structure in my head. Okay, and many of them just blend in. These two will blend into each other, and these two will blend each other. But these two at the top are not actually the same. They don't blend with each other. So think of it more of a weird, like, spectrum. But it is you've got short lifetimes to long lifetimes, but you can't have them. Yeah, you can see what I mean. It's like a weird thing going on. Okay, it's not hard and cut. It's more of you'll learn it as you go along. But then there's with regards to each of these kind of strategies, so let's go to the next kind of slide. Whoops, daisy. There's different types of allocators. So not the allocation strategies, but the allocators themselves. So an example of this, it's the most simplest one I can think of, is literally an arena. So an arena is just a block of memory. And you just allocate a big block of memory, and you just increase the pointer. So what this can be thought of is a big block, and you allocate your big block at once, you then, let's go, you do a block here. So you go block, you do another block, you do another block, and you do another block. You never free individual blocks, you only individual the entire arena. Okay? So that's one of the most simplest of allocation strategies. This is what I'll be using always, pretty much, for my permanent allocation. Now, there's two ways you can take an arena. The simplest way is if you run out of memory, what you're going to do. Well, that is a way to handle it. So the thing is, okay, what happens when I run out of memory? There is, what's the best way of thinking of this? So this question is, what happens when I run out of arena memory. So anybody in the chat have any ideas? I'm just going to let this to the audience. I already know the answer to this clearly because I'm planning it. But anybody got any questions, any ideas? What would you do when you run out of arena memory? There are multiple options to this, and I'm going to explain every single one and why they are quite useful. By the way, there are more than 3. There's a hint. Right, so the first person, okay, thank you, is someone says just make an arena. That's great. So I call this a growing arena. Growing arena. What you do is make a new arena block. So this is technically a subset of what I call a pool arena allocator. Okay. So your on has also said crash. Another option is just crash. That is a very good option. I would turn nil in this case rather than a nil pointer rather than crashing. Another option is to do a virtual alloc commit. So what this does is very clever. Exploit virtual memory. (64 bits are awesome. So that's one strategy. I'm just going to do these as strategies. Okay, so that's one strategy. Another strategy. So virtual alloc this is the OS. So this is an OS solution. This one is just keep reallocating new blocks. The other one is a nice little thing. It's called a ring buffer. Now this is not scratch memory, I would call this. So this is great for scratch memory, ring buffer is. So I use this for most of my temporary allocations where I only need it for a short period of time. I never free and I just let it go round and round and round in a loop like a carousel. So once I get to the end, I just go back to the beginning and overwrite what I did. That's a very good option. The other option is allow freeing, and we have a stack allocator. So last in, first out is the first one to put that in, or first in, last out, whatever you LIFO or FILO, whatever you call it. So this is where you allow freeing but but order of alloc/free matters. We get near the end of my thing. Okay, any other ones? There's one on this list. I think there's probably one more you could probably fit on this. Anyone got an idea? There is one more. Not an obvious one. I'm just going to drink some whiskey while I let people type because there's a delay on Twitch. Yeah, heap. I'm not going to answer that because I'll explain why in a minute. This is where I want. This is probably more than one article, by the way. But actually, it is technically an answer. Did I just say it? Yeah, so heap is kind of an answer. So you don't have any more... Well, a good way of doing this is reserve some of the arena to store pointers that were allocated on the heap. And I'm going to put the heap, actually no, allocated, I hate the heap, I hate the term, really do, on allocated with external allocator. I call this a subarena bookkeeping method. So you were correct when you said heap, but that's it. Your own Kalimian is saying that, yeah, you chain arenas. So that's kind of one way of doing it, is you kind of you have multiple ways of doing it. This approach with the bookkeeping, where you're going to chain things together and track with what happened with what was meant to be allocated in here, but allocated somewhere else. This is getting onto a bit more, starting to becoming a little bit more, not exactly, but closer to what a free list is. So this, hopefully this is making sense. Different allocators. This is just the basic, here's a block of memory. The ones I recommend most people to use are all of these except the bottom one, because there is a much better way of doing it. So this is what I would call sequential allocators. Yeah. Now we're going to call the next ones are the out of order allocators. Now the out of order allocators are quite complicated, and this is where fragmentation happens. So I usually nick them in my head, at least. Fragmented allocators. Now this is what most like malloc or things do. So one example of this is just malloc / I would say I'll say malloc. Malloc is a good way of doing this. So what is malloc? Malloc is technically very, very complicated. Yeah, so sequential is, contiguous is another good name as well. So contiguous, yeah, that's a very good way of putting it. Yeah, that's a good way of putting it. So malloc, most people call this the heap. Now, I'll go on a little rant for a little second. I really hate the concept of the heap. Now, this sounds bizarre to people, But I think this is the whole reason I want to do this article, actually, is that I hate how memory allocation is taught in general. I think it's people have taught it in an extremely abstract way. They're taught it as if the machine they're working on does magical stuff, which it does, and they don't have to worry about it, but they should. And it's like this weird dichotomy where you have the stack and the heap, and that's how it works. And you pop things onto the stack and it pops off. And it's like, that's just stupid. And it really is. Because at the end of the day, on most modern computers, everything is virtual memory for your program. Everything is virtual memory. So unless you're the operating system and unless you're writing operating systems, which you most definitely aren't, you are only having to worry about virtual memory in your head. And you treat everything as virtual memory. Now, the concept of the stack makes a lot of sense, and I will agree with that, because that's how procedures work. You call a procedure, it'll push stuff onto the stack, the variables that be used for that procedure, plus some other padding, for instance, like the prologue and epilogue and stuff. Then it'll handle that, and when that procedure's ended, it'll pop off the stack. That's great. That's a piece of virtual memory that is used for that program, which is just for doing calls. But I would class that as internal to the actual instruction set, in a sense. That's a weird way of framing it, but whatever. But when you're doing external, people say, well, that's just the heap we're now calling to. That's the memory out over where. And I'm like, that's stupid. You can literally still do allocations within that stack. The lifetime, though, is controlled by that procedure's frame. Like the procedure frame, the stack frame. That is the lifetime. But how you allocate with it is not any different. You can still treat that as if it was the heap, this idea of the magical heap. It's all just virtual memory. You can do what the hell you want with it. You can allocate. You could theoretically allocate. Let's allocate 4,000 bytes on the stack, and then we use those bytes as if we were using a arena, and we just treat it like that. We know what the lifetime is. It's just going to be that procedure's stack frame. That's all it's going to be. But you can still treat it as if it's any of this. Because it literally is. And we could technically say alloc A is also going to do this, but I don't want to complicate things up yet, especially for these articles. But yeah, so I know it sounds bizarre, but does that make sense to people? Why I'm not a big fan of actually this teaching people about the stack and the heap. It may sound great to beginners, but it doesn't actually explain how anything works nor how you should be doing things, or even it just abstracts things away. It's kind of bizarre. Okay, so let's go back to different out-of-order allocators while I remember how to do all this. No. Okay, so you're saying around about education. Education isn't technically it as well, but I'm not ranting about it. People get taught about this concept of the heap. The heap doesn't exist. Seriously, I know that sounds bizarre to people. The heap doesn't exist. Yeah. That's the best way of putting it. Yes, I'm just going to quote Clemian here in the chat. He says, the stack is real in the sense that there is a stack pointer in the ISA. There is no such thing as a heap pointer, and that is exactly correct. You have the memory that the OS that gives to you when you call virtual alloc, because the OS has allocated some virtual memory for you for that program space. There is not this magical heap that you allocate from. Yes, it is contiguous memory in virtual space. It's not contiguous memory in real life, but yes, it is a form of contiguous memory. And that's why I want to talk about out-of-order memory allocations. So everything is still contiguous, and keep that in mind. Contiguous is always key. So where's malloc? And we'll come back to this. So I wanted to just draw out I'm going to do this, actually. Let's make a little box with different type of lifetimes in it. These are different kind of stages within the program. Yeah, so you say, yeah, good, that's great. So someone's in the chat says, yeah, saying what I'm saying. Yeah, he says he's a cybersec guy. You need to know about memory layout and segmentation, though. And yes, that is correct. And it depends on what level of abstraction you're doing. I'm just talking about the average programmer who's doing memory allocations. And yeah, it is kind of useful to know how things do at the OS level, but it's one of those where you do things. So let's just do the example I've had before with the blocks. So let's say we have this, we allocate this block here, we've got another block here, another little slim block there, and another block here, right? So now what I'm going to do is actually put blue in there. Now on every single allocation I do, I'm going to put a little header on it. I'm going to signify with this blue. Yeah, they're all the same size header, regardless of the size here. So this is like the little header, yeah? Yeah? So this header will now encode the size of the allocation that is ahead of it, and maybe some other metadata as well. This depends on what the allocator is, but let's just say this is metadata usually just encoding the size of this allocation. Now, why is that useful? Okay? So what you can do is if you went to the allocator here, we could go through this entire list, yeah? And we could go read and say, okay, we go here and say, oh, we've got an allocation there. Oh, where's the next allocation? Well, it's here because we know the size of this, and it'll be at the end of this. Oh, perfect. We keep doing that, and we just keep doing this, yeah? So we can figure out where every single block is. Now let's say is, you know what, this block here we don't want anymore. So it now just becomes just this, yeah? We've now freed this empty space here. So I'm going to put ... for free. Now, you may think, okay, I want to come back again. I want to allocate something else. And you want to allocate a new block of memory, which I'm going to do in probably purple. Actually, no, let's just keep it in this kind of scent. And I want to allocate a new block here. And notice there's going to be a big gap there. Now, the way you can come across this is you can also store kind of store data about where the next allocations are in these headers. So just imagine there's stuff in there. Yeah? Yeah? So you've got this kind of blank spot in here as well. So these blank dots are free memory, and I could probably do that in green. So this is just, oops, green. So this is kind of free. The colours are probably the wrong way around, so who cares? And hopefully not colorblind. If you are, I'm so sorry. Now, you're going to do this, and after a while, when you allocate things and free things and stuff, you're going to have a lot of fragmentation going on. And this is a naive way of approaching things. So this is what happens when you're trying to make your own kind of malloc. Let's say you've got a fixed memory space, and you want to allocate some blocks in it. But you cannot move the blocks around because they have to be at a proper point. So the way is, how do you solve this? So one little solution is pretty much what this is doing, is a free list. And what you're doing is it's just a linked list saying where all the blocks are and when there's the next bit that's free and how big that free gap is and stuff like that. So then the next allocator, if you wanted to put in here, it was bigger than that gap, it would have to go here. Yeah? So you've still got these gaps here. Is this making more sense? Now, you've got this issue here, issue of fragmentation. So, if you are going to make a complicated allocator, this is a huge problem you're going to go and try and solve. Because fragmentation is a complicated problem to solve, and it is. And this is what you're doing when you're calling malloc all the time, in a sense. Imagining this is like a virtual memory address, and it's all fragmented, whatever. Hopefully it makes sense so far. This is literally just off the top of my head, not planned or anything. I am planning it now, clearly. So this is where your owner is getting a very good, is jumping the gun. What you do is, to produce this fragmentation, is never have it in the first place, which may sound bizarre as hell. What you do is you mix both strategies together. You mix the arena strategies with these block strategies and say each block. So what you can do is I call a free list pool. These are not the correct technical terms. I have no idea. My education is not in programming. I'm a physicist by education and profession. So please, please just, ignore what I class these are. So these are a free list pool. So what this means is block sizes are fixed width. Yeah. So what you just cheat is, instead of having allowed different sizes of blocks, you allow just say every single block is exactly the same size. So you have like this weird hierarchy. Yeah, that's a good way of putting it. It's a hierarchy of allocation strategies. Allocation strategies. So you kind of fix it together. So let's say you've got a block here, and you say you just allocate these blocks. That's one block, that's another block, that's another block, and that's free. And I'm just going to do these different generations again. So let's just make this quite long because I want to do different examples. Actually, ooh, that was actually a bad example. Yeah, so that's a bug there. And let's go for 2, 3. Yeah, I'm brilliant at drawing, can't you tell? So each block is always going to be the same size. Always. And that is the whole entire point. Right? So you have one pool, you allocate it here. You allocate another. And then we're going to just go again. So keep these blank. So green is blank. Yeah? We want to allocate another block. Oh, that's great. We just pop it off here. But now we're saying, oh, we're going to get rid of this block. Okay, so we've got red in there. That's dead. And that's alive. Then when we come to fill it, we can say this. Well, actually, no, I'm going to do that. Yeah. Now you can also free this and this and this, and that's green as well. And then you just start allocating again, like so, until you fill up all the memory. Is this making sense? Wiggly blocks are superior anyway. So once you've got each of these block pools, you can then do another allocation strategy. So in one of these blocks, so an allocated block can then do another strategy. Now that's pretty much it. You can pretty much use all those tools now just to do everything, and I mean that. Like, your biggest tools in your box for memory allocators are going to be arenas, stacks, ring buffers, pools, which I call, these are free list pools, I class these as, because you can, if you want to do this, it's not technically a free list, but it is kind of a free list. Free list pool slash slash arena pool, and you just do that. So yes, so someone's saying this is called a bitmap allocator. Now again, I do not know the technical terms, so thank you. Yeah, this is called a bitmap allocator. Yeah, that's literally what I'm talking about. This is exactly what I'm talking about. Yeah, you store all the information at the top, and yeah, that's exactly what I'm talking about. Thank you for the link. This is very good. Someone just get the link here. It'd be good. Buddy allocators as well. Yeah, they're pretty actually useful. But yeah, they're a little bit more complicated. But this is kind of a good introduction to do allocations, and the reason why I want people to think this way and think about how allocations happen is it's kind of like, you could say it's a Fortran way, where everything is just arrays, where these are just literally blocks of memory in a big array of just one giant memory. And the problem I want to keep getting down on this is that memory allocations and their lifetime are intrinsic. The compiler does not know the lifetime most of the time. You know the lifetime, not the compiler. The compiler can do the basic things, like for instance, the stack frame allocations. That's trivial. But it cannot do everything else. This is one of the reasons where, like, Rust tries to solve this problem and fails. And you may say, well, it does very well with all of its ownership semantics. But it's kind of one of those where it still fails if you want to actually get the proper performance, the proper everything, which is also regarded to the usage issue, because ownership semantics has no idea about usage. You're doing everything there. And even then, the lifetimes aren't really good, because with Rust, if it's going to be lazy, is once it goes it's dead, its lifetime is ended, it'll try and free it then, like it does with C++. So C++ is kind of like a stack-based allocation, where you've got the RAI going in. So once it's been allocated, once it's gone out of scope, it'll deallocate. I say deallocate's the wrong word. It constructs and destructs, not deconstruction. God, now we're going into postmodern philosophy. Well, not postmodern, it's close enough. Whatever. I'm very tired and not drunk, but just drinking whiskey. How does this seem like a good idea for explaining this kind of basic high-level overview of allocation? Does that make sense? Yes, Factor is deconstruction and planner, and it sends out the bots. Kind of, yeah. I should have used green and red the opposite way around now, thinking about it, but oh well. Hopefully this makes perfect sense. So this is where, again, this is kind of now a personal view and stuff, but this is where I think most languages have just gone wrong, like a lot wrong. And what I mean by that is they try and obscure memory allocation from the programmer, when at the end of the day, it's intrinsic to the programmer, which may sound bizarre for the average person, and the average person will disagree with me, and I don't blame them. This is probably an orthodox opinion, and it probably is, but oh well. But the way I'm trying to say this is, garbage collection, which is technically trying to solve this 1%, less than 1% problem, where you don't know the size of the lifetime of stuff. We're just trying to apply it to everything else, and then you're just going to have loads of issues with regards to usage and performance. And the usage is technically qual. I spelled qualities wrong. I said qualities. So this is technically, whoops, I'm using a pet mouse then. Perf, I'm putting perf in there as well. How things work. So then Rust is trying to go another approach, and well, actually, let's skip a bit too much here. So we've got, garbage collection tries to abstract memory allocation from the user, and that tries to let the language itself handle all of the allocations, deallocations, the lifetimes, the size, everything. And what it kind of does is what I do manually, in some cases like the generation of garbage collection, which is with the permanent allocation, transient allocations, and scratch allocations. This is what I do manually. And it's not a bad way of handling things. I'm not saying it's the perfect nor the only way of doing things. It really isn't the only way. It's just the one I've found to be most useful. I think this is also similar to what happens on Handmade Hero as well. I think Casey does permanent memory allocations and transient allocations. So it does that. And that's okay. So someone's questioning, has anyone tried something of a middle hand? No garbage collector, but some optional tool to help programmers manage memory. The answer is yes, but the question is, what do you mean? Now, I know that sounds bizarre. Odin does this where I allow for a context system where you can allow to put custom allocators on there and just allocate as if whatever the context uses. So it abstracts the allocator away, not the allocation. Now, some languages have reference counting. Some languages, so reference counting is quite an interesting thing to talk about. I should probably save this. Can I save this? Save. Yeah, let's move that. Yeah, it doesn't matter. Actually, none of that was personal. Actually, that's all right. Yeah, none of that was personal. Actually, some of that's really old as well. Wow, some of those files are old in my documents. Like, some of that's like, quite old. Where do I put this? Yeah, let's move this to... Let's do this for articles. Yeah, let's make a new folder for this. Let's call this... Yeah, I wanted to save this so I don't cock it up. So let's talk about... Now I wanted to talk about was this little quadrant here, which is you know the size, but you don't know the lifetime. So I want to call this... what's the best way? It's automatic lifetime. Automatic lifetime allocation. Note I don't call this automatic memory allocation because it isn't. It's automatic lifetime allocations. So the most common example of this is reference counting. Now this does not need to be automatic in handling it. You can do it manually. So you can just call a procedure where it says like copy pointer, and then when you delete it, you just dereference it. So you just pretty much increase the reference counting and decrease the reference counting, and then once the thing goes to 0, you can then tell an allocator to this is the way, it depends on what strategy you want to do for that. You can either say once it goes to 0, just say the memory's dead. The other option is you can wait for a short period of time, put it onto a stack, and then when you check it after that certain period of time, when it needs to be cleaned up, so it's kind of a garbage collector, if it is still 0, then you can kill it. If it isn't still 0, like for instance, someone might have just copied it again, then you can't delete it. So that's kind of a weird advanced reference counting. So that's more like a garbage collected reference counting, but it's still manual. God, that was weird to phrase. The other way of doing this is with ownership semantics. Actually, no, let's do a simple one. Let's do with RAII, which is in C++. So this is a constructor, destructor approach, which is kind of similar to reference counting in many cases. So this is scope-based. Yeah, the other one is ownership semantics. So this is examples of this would be R value references. R value references in C++11. You've also now got Rust and Rust lifetimes and stuff. / ownership. Oh god, there was another one, but I can't remember what it was. What's the other automatic lifetime allocation strategy I'm thinking of? Yeah, so someone is saying about other types of reference counting. So yeah, there are different types. So there is strong and weak. And then you have weak. And then you also have, I would call this pseudo GC. If that makes any sense. Automatic lifetime allocation. What else is there? There's another strategy you can use for automatic lifetime allocations. So the scope based is ownership based, which is once it loses ownership, it dies. Once this has lost any more references to it, it dies, depending on how strong, weak, or pseudo it is. Yeah, tracing GC kind of, yeah. But that's a different option. I won't put that in there. Just thinking, is that it? Is that it? Because that's not a bad kind of layout, in my opinion. You have this, 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 and this. That's about 2 or 3 articles already, in fact. But is there anything else with regard to any other ones? No, not different type of garbage collection strategies, but just automatic lifetime out strategies. So, yeah, so there is, that's what I mean. I don't mean, so mark and sweep, ever practical. Yes, technically mark and sweep is what the Go compiler does for their GC. So the Go language for the Go compiler, not the GCC one for Go. The Go one itself, the official one, uses mark and sweep for their GC. Many people said this is going to be slow. They've been trying to improve it more and more lately. And people said, look, many people who complain that Go is like stuck in the 70s with programming language design, which I don't think it is, nor would that be a bad thing, personally. But I do honestly, people say, yes, but your garbage collection design has been stuck in the 70s, and it kind of actually has. There's been a lot of technology and kind of like technical breakthroughs with regards to garbage collection, and mark and sweep is not one of them. Actually, is it mark and sweep? Actually, no, I'm a liar. No, it's not. It's stop the world. Oh, God. The whiskey's got to me. Mark and sweep. Yeah, that's tracing garbage collection. They don't do that. So I'm a liar. They do... is stop... I can't remember. Stop the world the same name. Just checking. No, they are the same. Yeah, they are... Sorry, they are pseudonyms. They are exactly the same. That's just me having a brain fart. Seriously, yeah, they're identical. Yeah, they're identical. Yeah, ignore me. So I could actually, yeah, this is not a bad idea of showing how mark and sweep works. That is really complicated when you think about it, and why that's naive, but it's not a bad way of understanding it. Tricolour marking. No, why is it tricolour? Oh, there's some graph theory, I can't remember. That does make a lot of sense, actually, when I think about it. Moving versus non-moving. Yeah. General racial GC, here we go. This is literally what I was talking about, what I do manually. And yeah, generation, you see infant mortality, generational hypothesis, and all that lot. And this is what I kind of say is most things don't live for long, and you as a programmer know their lifetime better than a GC could ever know. And this is why you should put them into different generations. So you have permanent, which is lasts for the entire program. Scratch, which only lasts for a very short period of time, maybe even shorter than the actual stack frame, or just slightly longer than it. You have transient allocations, which lasts for a certain period of frame, and then you can have stuff in between all those three. Yeah, so someone's asking me, how does NIM do their soft real-time GC? Now, I can't remember. I haven't actually read that part of the NIM compiler in a little while. But NIM's an interesting, actually, beast. So NIM was trying to be a new systems programming language with optional garbage collection in it. It's got manual memory management, but it's mostly automatic. But yes, I've been talking about all the technical stuff, I've just realised. I'm just reading a performance. Manual heap allocation. You just search for the best fit block. That was what I was talking about earlier, where you were talking about for the first fit is what I was looking for. The best fit is which you have to look through all the blocks just so you can fit one. Each strategy doesn't really make a big difference, but they're different things technically. Free list, yeah, you're just talking free list, which is you're managing things and scanning the site and chat. So that's just a bitmap allocator, yeah, if that's what they're called. Garbage collection says you have to locate all the reachable block. Yeah, there's a lot more in there. Determinism, yeah, that's another interesting thing to talk about. That's a good question. Yeah, that's quite useful. Because determinism is really quite interesting when it comes to programming in general. Yeah, so deterministic, reference counting is deterministic, but garbage collection isn't in general, which is quite, yeah, that's true. Which is why you can get, when you have like Stop the World, which is this mark and sweep approach, you have where it just stops just to collect thing, and that can happen randomly. And even if there's little amounts, you can. But then some people would argue, yeah, but you can just set it to predictable times, and then for it's deterministic, and that's not true. It just means it's predictable when it's going to do it. It doesn't tell you how long it's going to do it for, so it's not predictable. It's like, or some people say, yeah, we can get it down to very quick. So garbage collection is really fast now, and I'm like, I don't want it to be really fast. I don't want my garbage collection, I want it to be 0. That's why I do all the fancy allocations. Allocations don't even affect my time. I don't have to worry about them, which is actually the next parts of the allocation strategies I need to talk about. I don't know which order I need to do this in, so someone will have to help me plan this out slightly. Yeah, so this, yeah, I can't remember what the other one is now. I know there is one, but I can't remember what it is. It's don't think it's a very automatic lifetime allocation. Yeah, that's technically all of them. So you can pile everything together, by the way. The last time is regards to how to allocate. And I'm going to call this allocation grouping. Allocate in bulk. Free in bulk. What else do I need to do in this thing here as well as try not to think in objects / entities think in systems. So this is the other kind of little philosophy is very, very useful, and this is very useful in pretty much any field, I would say. So from games to writing software like science and stuff, which I've got to be doing next week anyway. I've just realised I forgot. I've got to be making some circuit boards for controlling some of the apparatus I'm building, and I need to make sure I've got all the components. Have I got enough MOSFETs for stuff and stuff like that? I think I probably do. If not, I'll just go to a shop and buy them. They're not expensive like pennies. The other thing I need to build with the other technology is, what else is I've got to build? What I've got to do? MOSFETs controlling a lot of the cores. I'm sorry, I'm just talking about what I'm doing. Yeah, I'm building stuff. Yeah, for work. But yeah, so. Yeah, pretty much. Even though I'm a physicist, I've now pretty much become the de facto electrical engineer at my job for some bizarre reason, because I know how to do all that stuff. Yeah, these are notes for making something. This is not an actual stream. This is planning. I want to make an article or a presentation, and probably a series of articles regarding multiple topics. And oh God, this is really hard to write on a computer. I'm not one of those that used to doing it all the time. So let's go through what I've talked about from the start. So allocation qualities, you've got to remember the size, lifetime and usage. So usage is regarding performance and how you are going to be using that code. This is a secondary concern and usually only worry about when you're optimizing stuff. And yeah. What kind of fixes do? I do, technically it's atomic physics and condensed matter physics. Yeah, so like Bose-Einstein condensates and stuff like that. Quantum clocks. What else do I do? Yeah, quantum clocks, atom interferometry and stuff like that. Yeah. Yeah, that's what I do. I cool atoms down with lasers. That's the best way of putting it. So if you could work full-time on Odin, would I work on it? Maybe. It depends on actually how much it'd be worth. Seriously, it's like, if I could make a decent living, and this is because Odin is pretty much a lot of research. It's really quite interesting, a lot with the research, and it's quite, I know it sounds daft, a lot of this is I don't think a lot of this has actually been researched into much with regards to language design. A lot of people have been going in weird areas and not been focused on the things that are actually practical. Like, for instance, I don't think Rust that's practical at the end of the day. Like, seriously. Yes, it's great. It can prove things for you if you're programming in the way it wants you to program in. But I don't want to program in that way. But yeah, whatever. I'm sorry, I'm ranting now. Someone else is saying is you'd use Zig or Odin, but you really want compile-time execution. I know what you feel. I know, and it's one of those things that I've been. What's the point? It's one of those things where I would have loved it, to be honest with you, but I think it complicates the language way too much. And not just that, but I'm trying to think of a good way of putting it. I want Odin to be deterministic, and the way that I would want to implement compile-time execution and make it feel good would not be deterministic anymore. The way that JI are doing it, I do not think is a deterministic way of doing it. Metaprogramming. John has, and I don't want to. I'm not trying to slag off John or anything here. This is a hypothesis. I don't know this for a definite. Is mainly because it's just that how he is doing compile-time execution in JAI or JI or J. I don't know how you pronounce that. Whatever. I'm just saying JAI at the moment. At the moment, my hypothesis is it's fundamentally undeterministic, and because of that, he will have massive dependency issues when it comes to cycles. And I've been watching some of the videos he's been doing, and he's been struggling. He's been trying to do all this, and my issue is I think he'll get 99% of the way there, 99.9% of the way there, and he won't get that 1.1%. So every 1 in 1,000 times you compile the same program, it'll come out with a slightly different result. And it's like, that's mainly because of how the way he's doing it. He's trying to multi-thread the semantic stage, and because threading itself is indeterministic because of the OS and how it schedules stuff, you are going to get serious issues. The bits where it doesn't matter where it's like you can definitely thread the lexer, you can definitely thread the parser stages. Yeah, I've done that in Odin already. You can thread the back end, multi-thread the back end. That's no issue. The problem is that channels is that semantic stage where you're doing all the type checking. Is that kind of needs to be in sequential and in order, and do it that way. So it's not technically the halting problem. I'd be very careful. This isn't the halting problem. The halting problem is it's related, but it's actually not the same problem. The halting problem would mean, the one way of getting around this problem is, the halting problem is that you just disallow recursion, you just disallow massive loops, you do certain things where if you do compile execution, you say what certain boundaries in, so you know it will stop in a certain amount of time. That's one way of getting rid of a holding. It doesn't technically get rid of the holding problem, but it lessens it, and it's just the same as if you had a normal compiler in general. But this indeterminacy isn't the same as the holding problem. It's regarding to what order dependencies happen in, and what times they get executed and when they get executed. And if it just changes just because of how the scheduling works I'm talking about limits to constant evaluation. And if you want to do it as crazy as JAI does with where anything can be executed at compile time, that's where the problems are going to hide. This is why most times when most languages like Zig is doing a very, very minor subset of the language in its compile time execution with the comp time things. I called this semantic macros, and I remember talking to Andrew. I don't know if he got the idea from me or if he just had the same idea at the same time. Probably the same idea. It's quite an obvious example with the semantic macros. But he limited it down. He's disallowed recursion in his semantic macros. He's disallowed a few things. He disallows loops going on for too many times and a few other things like that. And that's how he does it. I think reproducible builds are important for all cases, not some cases, all cases. So I think this is a hypothesis. I don't know if I'm wrong or right, just a hypothesis. And of course it's false survival, so you can test it. I'm thinking like a scientist. Oh well. But yeah. So let's go back to kind of the memory allocation strategies here. Yeah, so someone's saying is one thing that gets my nerves a bit is 90% of professional science videos talking about memory management follow the script of manual memory management is scary/hard. Instead of learning about manual memory management or different methods of allocation, let the GC take care of it. Talk about the upsides of GC, gloss over the downsides. I agree with you, but I don't think it's 90%. Depends on which area you're in. They probably don't even mention any of the downsides because, not to be rude, I don't think many people think in the concepts of trade-offs. They don't think most people think there's solutions. They don't think there's no such thing as solutions, there's only trade-offs. They don't think in that way. Honestly, it's like in most areas of their lives, they don't. Yeah. And I think the issue is that how people think, and this is a hypothesis as well, it's just my idea, it could be absolutely wrong. The only way to test it is to practically do it, is that I just think that that the way that people doing memory allocation strategies in general are flawed, and they're actually not even that difficult when you think about it. You have to just think about it in hierarchies. At the end of the day, your entire program is a directed graph in hierarchies pretty much, and hierarchical nodes and everywhere. Both. It's technically just a directed graph. Yeah. Whatever. So you can see what I'm going to do here is you have different hierarchies. You have these. This is one level of the hierarchy. You've got the continuous stuff. the out of order stuff, which is just another hierarchy of this. And then you have the automatic references, which is something else, which you can talk about the reference counting, which is, again, you can put this on another hierarchy of one of these. So can you see what's happening here? It's pretty much natural hierarchies arising from the different kind of ideas of splitting things down into smaller blocks, which naturally does like a tree or again hierarchy. Magic, it naturally arises by just doing that. And it's so easy to think it like that. I'm not forcing it that way, it just naturally arises. I just try and keep this as a very flat level structure, and that's how I think about it. I do not like adding hierarchies when they are not needed. Then we split this up and do it another little level, which then becomes a hierarchy. But I just think of it as flat. And that's the way I think most people should be thinking about memory, is you are just pretty much incrementing a pointer, and that's all you're doing. So I'm just trying to think of a good way of phrasing this. And again, this is just me planning and thinking out loud. Literally, I'm not kind of filtering what I'm saying. Is that I think abstraction is useful, but you need to prove that those abstractions are useful. And they are, most abstractions nowadays are not being proved. You have to be kind of like pragmatically empirical about this, or empirically pragmatic. I don't know which. Pragmatically empirical. That's going to see my philosophy. Yeah, pragmatically empirical. Even though pragmatism and empiricism are technically separate, but you know what I mean. I do not subscribe to the rationalist ideas, which is what kind of unfortunately is in vogue at the moment. With regards, we used to be object-oriented programming. That was the rationalist approach. Now it's gone to functional, because clearly it's all rationalistic. We can plan it out. We know we can get the type system perfect. Then it should help us out, right? From a priori. I'm like, you haven't tested that. These are tools you're writing solve problems with. Show how to do this in Odin. And the answer is, I will do, not today. In Odin, it's the same way you do it in C. The only difference with Odin is you just set what the context allocator is for this thing, and it works for the entirety of that context. That's it. Like, you can put your own custom allocator down and it'll work. Like, Odin already has a temporary allocator system, which is kind of a ring buffer, scratch memory. And I usually, at the beginning of my program, say, okay, can you give me, I don't know, 64K of memory for that scratch allocator, or even 64 meg if I'm really lazy. 64K, whatever. And just set it off so I can generate some big things, and it will just I'll free it at the beginning of every frame that I'm rendering on that screen, because I'm doing like UI stuff. And yeah, your own is good. You should know at least one level of abstraction lower than you work on, so you can make an informed decision about whether it's actually worth it. This is the case in pretty much any field, in my opinion, even in physics. So I'm quite well versed in quantum field theory and stuff, even though I don't actually have to use it most days. But knowing how it works and actually knowing how because I'm just using like bog standard quantum mechanics rather than going straight to field theory underneath, it's very useful to understand how that works as well. Like, you need to, again, it is one of those things where knowing the level of abstraction that you're on is great, but if you're going something wrong, you don't understand why it does that, go a bit lower. If you can. No, I don't have people praising garbage collection either. I think in some cases, like for instance, a web server, I think garbage collection is perfect in that case, which may sound bizarre to some people. If you have something where you need to allocate things, you literally, in a web server, if a lot of your allocations are in this less than 1%, like you literally don't know the sizes or the lifetimes, which is possible, seriously possible, garbage collection is perfect. This is why I praise the Go programming language a lot. It is designed for the purpose of making web server backends. And for a lot of the time they are in this little gap here. The problem sets they're doing is in this less than 1%. Their less than 1% is gone to pretty much their 4% slot. So it's this bit here has been shifted upwards. And because of that, it makes a lot of sense. That like 0.1% is close to 4%, which is 40 times greater. That is pretty serious to worry about. And hopefully this makes sense to people. So I think if I could turn this into articles, I'm trying to think now. So I've got 1, 2, 3. So you've got one article there. That's one article there, yeah? Then talking about but you could split these all into multiple articles, talking about how they're doing. Otherwise, this article is going to be huge. It'd probably need to be a series of articles then, wouldn't it? So we have, chapter 1, chapter 2, chapter 3, chapter 4, and chapter 5. That actually works out well. Yeah. So this is going to be 1, 2, 3, 4, and 5. And I think it makes sense to talk about it in that order as well. Oopsie-daisy. Because it does make sense if I think about it. So someone was saying this is kind of what I would call they call a bitmap, isn't it? A bitmap allocator. Yeah. Oh no, I've got one over here as well, and this is chapter 6. Let's put this in there. There's 6. So 6 chapters. Would this seem like a good chapter, like an article series? Does that make sense? 6 different chapters, and the different chapters, different sections. Yeah, I know it is technically free list, but I wanted to write that down as a link for myself as well. Like I wanted to write, I know it's called AKA. Like I just didn't know the name. I didn't know it was also called a bitmap. Yeah, free list is the same thing. Yeah, that was just for me. I didn't know that was another way of calling it. Isn't the best memory allocation strategy just buy more memory? In some certain circumstances, that is seriously an option. That's not even a joke. When it is more cost effective to buy more memory than it is to handle the memory, buying more is not an issue. But sometimes when you cannot buy more memory, or you're in a limited memory environment, limited could also mean like you've got gigabytes of memory. That's still limited. Then you're gonna have to worry about how memory is allocated. But if you really don't care about how it's all going to be done, buying more might be cheaper. And this is what a lot of web companies do, where it is a lot cheaper to just buy more memory for their servers than it is to just actually write better code. It takes less time to do, and they don't have to worry. But that's only an issue if they're sloppy with how big their allocations are. So in that regards, going back to this is why actually it's not bad, actually not a bad way at all of thinking about this problem, is they don't really care about the size. They know the lifetime. This is how they do everything. So the lifetime bit is fine. They do not know the size of their thing. So this entire column is what their domain is. So they're most likely in these 2 categories. Yeah? And it may just be cheaper for them to not. So for this extra of, let's say, 4% of the time, the allocations, it's cheaper to buy more memory than it is to pay programmers to make it more obvious. It is just an economics problem at the end of the day. It is what is on the margins the best way of doing this. But yeah, it works. It seriously does. But this is also one of the reasons why big companies don't really care. It's also why your phone is very slow, even though your phone is literally a supercomputer. You've got applications that hog down the memory and stuff. You could say there's the ethical aspect. I don't really know which bit of the ethical aspect you mean, as in it maybe the user experience is not good or anything like that, maybe, but I don't think there's actually an ethical aspect with regards to buying more RAM rather than paying the programmers to actually make it better. I don't think that's actually an ethical aspect. Unless you, well, it is. Maybe it's not a good show of character in the fact that you've not actually worked your team well to make it actually have that problem in the first place, but it is cost-benefit analysis. Yeah, maybe in that regard it's an ethical thing, but it's not really. I don't know, not ethical. Most people talk about ethical nowadays. Yeah, most people nowadays talk about ethics as regards to justice, and it's just I'm not going in that. Believe me, ranting about philosophy at this moment. So next, another thing. So ideally, you want to make sure how do you say useful density is close to 100%. So your memory is not like Swiss cheese. Different methods and different work have different characteristics. Yes, different problems have different trade-offs. That's a simple way of doing it. Different problems have different data sets, different tables, different ways of analysing the code. So someone saying, no, the ethical aspect of making software that squanders resources, which makes programs run slower and drain batteries. I don't think that's an ethical problem at all. I think that is mainly well, it is an ethical problem from a character standpoint. It's not an ethical problem regards to an individual character like, yes, people are lazy when they come to making programs, and it's very bad. That's the whole reason why handmade movement came about, because we got annoyed by this because we think software is shit. So it is and yes, it is an ethicalness of wasting users' time. So yes, it is bad character to do this. This is wrong in the fact that you are not making a good product. You should be making a good product for your users. And just because it's just good enough doesn't mean it is a good thing you're doing it. But the reason here is, how do you solve this problem? If you think this is a problem, how are you going to solve it? Or at least lessen it. And the problem is, what incentive do these programmers have? It is a thing where it's the programmers or the companies themselves would only have to have guidelines, and they'd have to kind of have a moral code of how to do things. And first off, I don't really trust companies to do that in the first place. I don't think companies at all should be doing anything with regards to social planning. In that regards, I think what a company should be doing is producing money for their shareholders, and that is literally it. But yes, I won't go there and talk about economics. But with regards to, yes, it's more on the onus of the individual of the programmer doing it themselves and trying to be taking pride in their work and making it better. But again, it's people work on incentives. So what incentive have they got to make good software? And how are you going to do that? And the problem is, with regards to programming at the moment, in the current present, there is no incentive. None. Computers are so fast, so we can be lazy. Is it Andy giveth and billeth take away is the old phrase, where Intel would start making better and better processors and stuff, and then Microsoft would just go even faster and make it worse, and just use it all up and make it slower, because memory and processor speed became so cheap. So there was no incentive to make it go faster, because look how good everything's going faster. Can you notice the problem? It's an incentive problems at the end of the day. So if you can solve that incentive problem, your ethical problem disappears. And of course, it completely adds up. Like, you can, just one program, and then you've got another one that's very slow, another one that's slow and slow, and you're trying to use them all together, and they're exponentially slower. And it just starts getting crazy. And then you think, why does this program need so much memory? Like, why does Google Chrome need a gigabyte per tab or something stupid? And I'm not joking, sometimes it will be that much. And why is it boosting up another instant per tab for its Google Chrome? I'm like, it's not even another process. It's like another instance sometimes. And it's like, what the flipping hell is going on here? And not... Oh. And like again, as I said, why does the OS need that much RAM when it's doing nothing? And that's a good question. I have no idea. But it is the issue of there is no incentive for them to not do it, so they'll keep doing it. There will come a point when computers will not be getting any faster, and it's getting there now, where the computers are single processor speed is it's not increasing anymore. In fact, it's probably slowing down, but we get more processors. So now we're going to have to start multi-threading everything. So someone saying Moore's law is kind of stopping. It depends on how you define Moore's law. If you're defining Moore's law with regard to the size of transistors, then the answer is yes, because we're reaching the physical limits of how small you can make a transistor without the quantum effects transistors work through quantum effects, but yeah, the quantum effects of the transistors, how they work, it starts things, literally the electrons just start jumping into the other transistors, and then it just cocks everything up. Because that's how actually a transistor works. It is a quantum tunneling that's going on. So these are like a probability density where the electrons can go, and they will jump across the barriers, in a sense. That's kind of... I'm trying to dumb this really weird down without people knowing how quantum mechanics works. That's how a transistor works, like small ones. So when you get them very, very close, that means the probability density of where the electron will be still even wider. That means they'll actually probably overlap into the next transistors, so they can actually affect the next one. So yes, you can probably make not single atom transistors, but probably multiple atom transistors. But yes, so someone's saying it's not the number of transistors per dollar, but it's per the dollar, but not speed. So that's the other thing I was about to say. And that was how you do it. So someone says, does incentive mean financial incentive? No. Incentive just means incentive. Financial incentive is a type of incentive. It's just incentives. Like, that's how people work. Why do we do anything? Seriously, why do you do anything? Why do you get up in the morning? Because you want to do something, and why? Because you enjoy it. That's the incentive. In humans, we have this idea of means and ends, and we want to achieve it. It's kind of just built into us. It's a very weird thing. Animals kind of have it, but not the direct means ends purpose, also purpose driven thing. I don't know why I'm going to philosophy. When I get probably it's just partially drunk, and that's how I go there. You like read the newspaper? Well, good. I sometimes do as well. Not always newspapers. There's not that many good newspapers nowadays anymore. It's quite annoying. There used to be quite a lot of good ones. Only like even 5 years ago there were some good ones, and now they're all a bit shit. Yeah. So someone's saying at some point some new software will come out that does things so much better than everyone else that the rest will more or less be forced to do it because the users won't accept much. Yes, so this is kind of... you could class this as the last way of thinking about it is called a paradigm shift, where that's not derailing actually. This is quite interesting. It's kind of a bit of philosophy where things will have a big paradigm shift and things, and then everyone else is trying to catch up to do that, to get into that thing. So a great example of this would have been the iPhone. So before the iPhone, all phones were pretty much simple. I mean, people had flip phones. There were the odd smartphone around, but people didn't use them because they were no real better than having a flip phone and then having an iPod and separate things. So when the iPhone came around, it was literally revolutionary. And that's where it's kind of thing like that. Not just that, the iPhone is not just the only revolutionary thing, but something like the calculator was a revolutionary, the personal computer was revolutionary, the World Wide Web, not the internet, but the World Wide Web was revolutionary, and things like that. And it's sometimes you may think these are new technical boundaries. You have these new paradigm shifts where new things, and then the other companies will try and compete to get to that thing, and eventually they'll start saying like at the moment pretty much Like, for instance, the abacus and slide rule revolutionary too. Exactly, yeah, and that's not even a joke. Like, you see some people using abacuses today, and bloody hell, they're fast. Like, I know in like they're still being taught in like Eastern like countries, like in Japan and stuff, and China, and they still get taught on abacuses. And you can see some people pretending they've got an abacus there to do mathematics with their hands, and it's like they're stupidly fast. Whoa, that's so cool. And you can do square roots and stuff on abacuses. It's like, what? Like, I know, but yeah, whatever. I know I'm not got anything on the screen now. You just hear me ramble. And how long has this stream been going on for? That's a question. Is that not how I do it? No. Oh, time. Into what? 1 hour and 30 minutes. It's all right then. But yeah, that's pretty interesting. But that, who did the paradigm shift stuff for science? Was it Quinn? I don't know how to pronounce his name. I think it's Quine, isn't it? His name? Yeah. Because, yeah, his idea was notable ideas. Is it Quine I'm thinking of? No, it's not Quine. Who am I thinking of? He's a naturalist, isn't he? Paradigm shift. Kern. Wrong one. So many different philosophers. There's getting head. Kern. Thomas Kern. That's who I'm thinking of. There you go. That's the right one. Look at his sideburns. That's who I'm remembering. Sorry. Quine was a naturalist. Got those mixed up for some reason, even though they're nothing alike. Yeah, he was talking about paradigm shift, which was another way of thinking about things, about how science comes along. I'm not a big fan of the paradigm shift idea, to be honest with you. Well, I am, but I'm not. It's got issues. I don't know why I'm going down here, but it's got whatever. Because paradigm shifts aren't necessarily good things and bad things either. Like, for instance, in economics, the Keynesian revolution typically viewed as a major shift in macroeconomics. That's completely true. According to John Galbraith, Say's law dominated economic thought prior to Keynes for over a century, and then the shift to Keynesian was difficult. It wasn't difficult, even though Say's law is still correct. Okay, I'm biased there. Say's law is correct. Keynesianism is wrong. Ooh, what? Oh, whatever. Contrary law implied that underemployment is virtually impossible. That is not actually true. That's not what Say's law states, technically. Yeah, that's not technically what... It means that in equilibrium that is impossible. Yes, non-equilibrium, that's where Say's law is pretty interesting. The monetarism, which is technically a subset of Keynesianism. I don't know why I'm reading this. Yeah, it's just... monetarism is actually a compromise of Keynesianism. It's not technically... It's still technically in the Keynesian framework, even though they're trying not to be Keynesian. Yeah, so I don't know, it's interesting. What else they got? Cosmology, transition in cosmology from polemic cosmology to Copernican one. Which one's the polemic? Geocentric model, yeah, okay. Exceptions to work, errors, Galilean. Then, from transition from Aristotelian mechanics to classical mechanics, yeah, that's true. So... Yeah, so that's interesting because Aristotle was one of those things where I'm a fan of Aristotle, but when it came to mechanics and stuff, oh God, was he wrong, and extremely wrong. Like, and I mean like when it comes to like physics and stuff, like when it comes to motion, because he thought, for instance, here's one thing that says, he states that objects fall at a speed proportional to their weight in a liquid, and inversely proportional to their density. Now, this is only correct, it said, yeah, it's only correct within, like, air and water, because one thing he did not take into account is that it's not density, it's viscosity. I'm taking a break here. But Aristotle, I do like the man. But yeah, he got that wrong. There's also, for instance, he thought things had impetus and stuff like that. So, like, for instance, he thought things fell out the road when they ran out of impetus, so they just fall. Like, but the thing is, the average archer would know that wasn't even correct, because he knew archers, when you pull a bow, it would fall into a parabola shape or an arc. That was the way I thought of. So clearly it wasn't impetus theory, and they knew that intuitionally, but Aristotle didn't. Because this is where the idea of the objects require an impetus, they keep something to keep them going. While Newton had the opposite idea, that things would just keep going unless they told not to do, which is the first law of Newton's first law. Things will just keep going at the same rate, unless acted on an external force. While Aristotle's idea was that it needed something to keep it going, and if it didn't have that, it would just stop, in a sense, if that makes any sense. Now, that idea of things keep going is also a kind of idea of, related to his ideas of causation and first cause and stuff like that, and it's interesting, actually. It's quite interesting. I recommend it. What else is that? I'm just looking through this. It's quite interesting. Voisier's theory of chemical reactions, so from the phlogiston theory to the chemical revolution, yes. Things aren't... great stuff. It's completely wrong. But what else is that? I'm just looking at else here. Optics. Transition from geometric optics to physical optics with wave theories. From Fresnel. It's Fresnel. Hyperbolic geometry was discovered. Yes. Revolution in evolution, which is Charles Darwin. So it was natural selection, which is the bit. Evolution wasn't the controversial bit, it was the natural selection thing. What else is germ theory disease? Yeah, it's quite interesting. Quantum mechanics, yeah. Quantum mechanics, fun fact, was discovered because they were trying to figure out how ovens worked. Not a joke. They were trying to figure out, it was Planck, in fact, was trying to figure out why the distribution of temperatures of things within an oven, like a black body is a technical term in that sense. And the way he did it is he was just doing a cheat. He said, okay, let's just put this constant in here and just do this. And he couldn't get rid of it. It was just like something he put in, thought he could get rid of later. And it turned out that things that actually had to be, he had quantums of energy, like a quantas, where they had fixed energy packets of things. And this is where the quantum, single item bits come from. And once he did that, it made more perfect sense. So it was literally just trying to figure out how ovens worked, literally, and then quantum mechanics was discovered. Fun fact: the idea of luminiferous ether replaced to the space, present in space to the electromagnetic radiation rate in space-time. So the idea is that people thought things had to have a medium for something to travel through. Which is technically correct, but it's not correct. Like, things had to be in a medium for them to travel. Like, sound had to be traveled through air or water or something. So light must have had to go through this magical ether. This luminescent, I can't even pronounce the word, but an ether, well, light had to travel through that. Because, like, sound was through an air, and we knew that light was a wave, so it had to be through a medium, right? But that isn't true. Because light just is. Then we figured out that there's actually just like waves, like fields, like there's an electromagnetic field that permeates space and time, and the light itself is it's a photon that propagates through that field. Even though fields probably won't. That makes sense. Yeah, trying to do the pictures, and it's propagating through that field, in a sense. So the last paradigm shift was 1919. I'm not a big fan of paradigm shifts in general. You could also say there's quantum field theory was another one after that, and stuff like that. There's also the ideas of quantum and general cosmology in general, which is later on in the 80s. So I'm not a big fan of these paradigm shifts. I'm not. I don't really think of it that way. I don't know why I'm going into this bleeming thing anyway. But what was the questions that people had with regards to? So Aristotle was the first tip. He thought everything was alive and had feelings. Not exactly. He thought everything had an essence. So and there was different like different things of essence. Like humans were reasoning beings and had that sort of levels, and they had animals which had another essence, and species like plants had another level of essence, and like vegetation and stuff that. And then before you had rocks, which is a different type of essence. It wasn't really essence. Wasn't a soul and alive. It kind of is, but it's not. Oh, it's confusing. It's very hard to think in ways you don't think about. So you were talking about other things. Is the issue I'm referring to is that GC is most cases tends to jumble things around, making the cache less useful. That is correct, because what the issue is with GC, as we talked about earlier, is fragmentation. And this is where generational things is like the generational hypothesis, which I don't think is a hypothesis in practice. It seems to be the case. I know this from experience by doing it manually. You definitely need different generations of handling this to get rid of the fragmentation. And then the cache, this is regarding also memory usage, because you know how we need to worry about the size and the lifetime, and also the contiguousness would help the cache as well. Yeah, so, and I think if we're going to talk about paradigm shift, because it's not a bad idea, is that there is always when you design programs originally, like programs in general, you were kind of doing it with machine code straight away, just raw machine code. Then there was like kind of this level of breakthrough. We had assembly language, so we abstracted that above. We turned that machine code and we had an assembly language where it was kind of like, hey, this instruction has a name and we can put it into English. That was kind of a revolutionary step. The next after assembly language would have been something like C. Now C is a new kind of big step forward. Now, and again, C allowed you to do basic operations. I wouldn't have to worry about the... you didn't need to worry about... many of these allocations or the registers and stuff like that. It was made good. Now, Fred Brooks posited a conjecture. He said that there will not... Each of those gaps that go from like machine code to assembly was an order of magnitude more higher productivity, and assembly to C was more order of magnitude higher productivity. He posited that there would probably not be in the foreseeable future, or probably ever, another language that would be a order of magnitude better. That means like 10 times, whatever you want to class an order of magnitude as, better productivity than C was. And I'm finding that to be the case, really. Like, that seems to be true. And this is where I'm trying to think, okay, if we're not getting order of magnitude by language, maybe it's not the language that is not the issue. Maybe we've gotten to a point where humans themselves, that's the highest we can actually think about in the programming languages. Because that might be actually like the physical limit in our brains, because... like human languages, if a language gets too complex, we slow down. Like English is a quite slow language because it's actually quite a lot. There's quite a dense amount of information in there. Well, if you're speaking French, it's quite a fast language in comparison to English because it's not a very dense language. There's a lot of redundancy in it. So program languages may have that similar issue in the way you're thinking about it. So someone had a question about some physics. So if we had some kind of quantification data enabling long-distance data transfer, my guess is the local speed of time would have some sort of effect of reading that data at both ends. One side would need to be able to read the quantum stream. Not exactly, because there is not... information is not the same as other things. Oh, I'm not going to... That's a bit complicated to actually talk about. But the answer is no. AI, talking to an AI, no, that's not going to be helpful either, because you've got to remember, you talking is a way of communicating stuff, and that is just going to be as slow as you as programming it. And you conveying an idea clearly in English is not going to be very well. That's why we have programming languages. You do not write programs in English because English is a very ambiguous and unclear language. It doesn't make much sense. If that makes any sense. Now, you're saying is you could, by the way, in case of sending and receiving information to a drone in a black hole, so you physically couldn't do that. Once you've gone past the Schwarzschild radius, even light cannot escape, and information travels at the speed of light. That's the speed of light is the speed of causation, pretty much. And that physically cannot happen, because once you pass the Schwarzschild radius, the event horizon, you have reached the point at which, to escape that, you need to go faster than the speed of light, which is not possible. So therefore, you cannot communicate anymore. And there you go. That's pretty much it, yeah. So let's go back to this topic here of the allocation strategies. Can anybody else think what else I could add to make this a really good article series? Or series of articles. Yeah, series of articles. That's a better word. Does this make sense? Anybody questioning this with the allocation strategies? So we've got the quality of this, we've got the size, lifetime, and usage, different percentage of times. I'll also put that this is domain specific. Web stuff is usually size unknown column. So we have different this. So you could call this generations. In this case, these are the different type of generations. Because that's it, the lifetimes of different generations. So you've got sequential allocators, so you've got arena block. So the arena is just a block of memory, and that's how you can think about allocations. You can just keep allocating to the end, never free. So the question is, what happens when you run out of memory? You can just grow another arena. So this is kind of a subset of a pool allocator, which we talk about here, but it's a different hierarchy. That's just so you want to make pretty much another arena block, probably of the same size or something that's big enough to fit the next allocation in. Another one is you could treat the arena block as just as a virtual alloc, so you commit more memory and you just exploit the virtual memory, how it works. So the virtual memory pretends it's just linear memory, even though internally the OS handles all that. Again, 64 bits of memory is amazing. So you can just literally commit. Say, okay, can you reserve? So yeah, you can reserve loads of memory. Loads of memory. You can just reserve a terabyte. Seriously, you may not have that much memory, clearly. Or not a terabyte. You could say you could technically, and just commit it when you need more. Never free. I know it's technically 48 bits. I know, but 64 bits are great. Ring buffer. So the ring buffer is great. So instead of going to the end and creating more memory, just go back to the beginning. So it's great for scratch memory. Stack allocator is good because that means you can then you pop one block on, you get rid of it, and you turn it back. So you can keep going back and forth on this thing. But you can only go forward and backwards. You can never jump. So it's very useful to have. Again, this allows freeing, but only if the order of allocation matters. So it's not out of order. The other one is you can reserve some of the space in an arena that stores pointer to where you've extended in a second allocator. So this is a bookkeeping approach. So you'd have this approach here is you've now got, this is the reserve for bookkeeping, and then you allocate blocks in this thing. So like that, yeah? Makes sense? So that's bookkeeping in there. So you reserve a bit of memory just for the bookkeeping, so you can do it on an external allocator. So this could be, in here you've kind of got different pointers for when it's full, and they can be pointed elsewhere. Whatever, that looks really weird. But yeah. So the next thing is out of order memory. So let's say you want to be able to free blocks of memory because you don't want it, but it has to be out of order, so you can't use a stack anymore. This is usually, sometimes this is the case. This is not always the case. Be very careful. You can sometimes rearrange your data structures where you can use a stack. The cases where you cannot always do the out of order stuff is like something like you need to resize an array and you don't know how large it's going to be. You can do that with a stack and arena if there's nothing else allocated afterwards. That's sometimes a problem, and that's where you need out of order stuff. So this little free list allocator system here was quite a good simple example. You got little headers at the beginning of everything telling how what the size is and where the next free thing is. This is also called a bitmap allocator apparently. And then you just allocate blocks at a time. You've got free memory. So you free these blocks and that's free. So when you need another one, you need to find the best next fit. So this could fit in there, and it's still got fragmentation. You need another one, so can't fit in there, so I'll have to go over here. And you've now got loads of fragmentation going on when you've freed stuff. It looks horrible. So you can fix this by having fixed width allocation blocks. So you can call this like a free list of pools or an arena pool where each block is the same width and you allocate to each of the blocks. So you don't have to worry about having... you don't have to have headers anymore, theoretically. You can have an allocation system where it handles where the blocks are at the start, so you can have a the other bit of the memory where that handles and then other blocks afterwards, which handles all of the management rather than next to the data. But then each one, when you free it, it will just fill up the first one it gets handled. Like here, we're going to do these two first, then those are free, then we'll allocate a new one, that's still free. We free the second one, those are blocked. We free the first one, that's still blocked. So when we add two more in, that'll be up, and then add another one in, the entire thing's done. So within these blocks, you can do other allocation strategies. And within these blocks, so for instance, you're not just limited to the different blocks, and that's all you can do. Is then within one of these blocks, you can think of that as another system. Within this system, so it's another subsystem, where you could just go for a simple stack allocator or a ring buffer, or you could each have these as be the growing arenas, which is why I said this is a pool allocator, where each of these is an arena, and this will be the next in the pool. And you could free each of these arenas, and then you've got this pool done. That's exactly what could be going on. The other thing which I wanted to talk about, which are completely separate now to the strategies, is that you can... By the way, there's a lot more complicated ways of doing things. That's why I put malloc at the front, because malloc does a lot more strategies than this. Then you have automatic lifetime allocations. So I do not call this automatic memory allocations, because memory to handle size and lifetime doesn't handle the usage. The language can never handle that. You have to handle that, clearly, by definition. Automatic lifetime handling, so one option is reference counting, so you don't know the lifetime. So there are three types: there's strong, weak, and pseudo GC. So strong means it can not have references to anything else, so you can't have loops. Weak means you can have loops with referencing, so if something references another thing and it's got a loop, like a cyclic dependency, they'll keep both each other alive until they're both killed at the same time. Pseudo GC means you need to kill that thing after a certain point. Like it may get to 0, it gets added to the list of checking to get killed, and then once it has been, when it comes to check, if it still was 0, then you can kill it. If it's not 0 yet, like it may have been added straight away afterwards, then you keep it alive. So this is like a pseudo GC for reference counting, if that makes any sense. This is a kind of, it is kind of like a mark and sweep, but not a mark and sweep, if that makes any sense. It's more of a, that's why I call it pseudo GC. The other one is like RAI and C++, where you have scope-based stuff, where you have constructors and destructors. And you can do it by a scope base, and you can have all the like copy constructors, move constructors, but the move constructors is also when it comes to ownership semantics. So you have all reference values in C++, or just Rust lifetime and ownership in general. Someone's asking the question, assuming that the first part of the problem is solved, you have the problem of one person needing to wait longer to give the other guy time to read it. Yeah, that's what I mean by pseudo GC. So, assuming it has been freed, no one else is killing it, using it, that's what that waiting period is to check it. So you say, yes, you need to wait longer than the other guy to read it. That's where that's why I call it pseudo GC. You need to make sure that you know when to check it. Yes, you do have to worry about it being longer than the next time reading it. That is correct. And if that isn't the case, then you've fucked up somewhere. And that's not going to be solved by any of this. Like, not a joke. You're not going to be able to solve that. Just not a problem. Okay. Oh, you're talking about something completely different. Okay. So, all right. But it seemed relevant. Then you have ownership semantics, and that's good. I won't talk about what the advantages and disadvantages are, just that they exist. And 6 is kind of a general motto of allocation grouping. So allocating bulk, free and bulk. Try not to think in single objects or entities. Oops. I'm going to call this a night in a minute. Singularly. Think in systems. I'm going to call that pools. I think. Does it save it automatically for me? Yeah. That seems to make sense. So he's saying, does heap allocate store the header in front of the block? The answer is yes. 40 bytes is not bad, to be honest with you. 40 bytes doesn't make sense. Yeah, it makes sense, because you're going to probably use 8 bytes just to say what the size of your allocation is. You can use another 8 byte. Yeah, you can use 8 bytes. Yeah, 5 words. Does that make sense? Yeah. I think I'm going to call that a night. If you've got any other questions, I'll be here just for another few minutes, but please get those questions in, because I am literally going to go to sleep. You can see what time it is. I'm going to be tired. Yeah? So that's my little overview for the different chapters in this series of articles that I want to write. I'll probably need to write them in order. I might merge these two together, actually. So merge. Oops. But yes, any other questions? So this looks good, yeah? So someone's saying about, okay, so why can't, okay, this is a physics thing, so why can't entanglement use to cheat light speed for faster comms? The answer is information, causation, that's the idea, cannot go faster than the speed of light. Entanglement is instantaneous, but here's the funny thing. You can, let's say you have two entangled particles and you move them very far apart. You measure one of them. When you measure it, it forces it, you can say it goes into a state. I'm not saying it collapses, you can say it collapses the wave function. That's one way of thinking about it. If you don't do this collapsion of the wave function, then it's a different issue. But let's say I'm just going to do the Copenhagen or semi-Copenhagen with the more consistent histories form, at least, where it collapses the wave function, it goes into one state. That you could probably, this isn't technically going to be consistent, So that's the first thing. It'll just be probabilistic. So whichever way you measure it, and you know it's going to be, it's entangled with another like thick quantum system, like say a particle. You know it's going to, say it's going to be the opposite to what you think, or you know it's going to be some correlation to it. The thing is, you can never know for sure until you make a measurement with the other one. So if someone else measures it and you measure the other one and they measure the other one, the only time that will make sense is when you come together and you put your information together. So you've never actually communicated any information until you've come and brought it together. And that takes, and you can only do that as fast as at the speed of light. Yeah, there's the trick around quantum entanglement. Even though it happens instantaneously, which is the interesting thing, it's the acting of measuring the thing itself, which is the thing you need to do. So yes, even though it happens instantaneously, when you measure it, your information transfer of the measurement is not instantaneously. Does that make sense? I've probably butchered that, trying to dumb it down. But does that make sense? Someone's asking me, what happens when after you die? No fucking idea. Go ask your priest or bishop or guru or shaman. I don't know. Whatever. I'm an atheist. I don't really know. Agnostic atheist is the best way of putting it. Yeah, probably whatever. So does that make sense? Yes, so the issue when it comes to quantum mechanics is measurement is a thing we don't actually understand very well. We don't actually. A measurement is all to do with measurement. So you can only transfer things, technically, you can only transfer useful information at the speed of light. That's the fastest you can do it. So a way to explain this is that you've got a laser, let's say you had a laser pointer, yeah? And you pointed it at the moon. Like if you're on the Earth and pointed at the moon, that light is going to take about 1.5 seconds to get to the moon, right? Now here's the fun thing. You could flick your wrist so it points from one end of the moon to the other moon, and you flick it and you're like a fraction of a second. Well, the arc time it's taken you from that fraction of a second, the time it towards the moon is going to be faster than the speed of light. But here's the fun thing. No useful information was transferred when you flashed it, because the light is going to be following still at the speed of light in a wave. So the signal wave is faster than the speed of light, but the phase wave is going to be faster than the speed of light, but your signal, the actual useful information, is not any faster than the speed of light. That's a good way of thinking about it, probably. So like flicking a laser pointer across like the moon from one side to the other, you're doing it with the flick of your wrist. Literally that thing looks like it's going faster than the speed of light, but it isn't. The information is not being transferred faster. Okay, that's making more sense. I don't know why this has turned into talking about memory allocation strategies, philosophy of programming, philosophy in general to physics. But there you go. It's just turned into one of them. So welcome to Odin. Yes, this is random. My brain is like this all the time. So thank you for listening and good night, everybody. Goodbye.